Ever feel like you're drowning in information, trying to grasp these complex topics, but it just feels overwhelming?
I hear you. It's like trying to drink from a fire hose sometimes.
Exactly. So today we're cutting through the noise, going deep on something called chemoinformatics. Using computers to tackle those big chemistry problems.
It's basically harnessing computational power to really understand the chemical world.
Yeah.
I mean, we're talking about everything from how molecules are structured to how they behave and interact.
Okay, so it's more than just like, digital chemistry notes. What are we really looking at here?
It's like this. Imagine having these giant digital libraries, think PubChem or ChemSpider,
Yeah.
packed with information on millions of compounds. These databases are the foundation.
Got it. So we've got the information, but how do we actually work with it digitally?
Well, we've got these clever ways to represent molecules digitally, like using smiles or InGi codes. Think of them like molecular barcodes.
Okay, so it's like a universal language for molecules, right?
Exactly. And we've got software like RDKit and OpenBabel that act like translators between these different formats. Pretty amazing. And once you have this digital representation, you can do some really cool things.
Like what? Give me an example.
Well, take QSAR, for instance. That's where we use statistical models to connect a molecule structure to its activity. So imagine being able to predict how effective a drug might be just by looking at its digital code.
Wow, that's powerful. So we're predicting how things behave in the real world, all from a computer.
Precisely. And then there's molecular modeling and simulation. This is where things get visual. We can actually see how molecules interact at the atomic level, all thanks to computers.
So that's got to be super helpful for understanding how drugs work in the body, right?
Absolutely.
Mm.
And then, of course, we can't forget about data mining and machine learning. These techniques let us analyze huge data sets, find hidden patterns, and build predictive models. It's like having a superpowered research assistant.
So the computer becomes this incredibly efficient researcher, helping us pinpoint drugs, for example. You mentioned that was a key application of all this.
Yeah, it really is. Take drug discovery. Chemoinformatics is a game changer at multiple stages. It can help identify the right target in the body for a new medicine by analyzing biological data. That's target identification.
Right. And then, of course, there's actually finding the drug itself, the whole discovery process.
Yeah, that's where lead discovery and optimization come in. Using techniques like virtual screening and QSRR, we can find promising molecules and fine-tune them, making them more effective and safer.
I can see how that would speed things up significantly. But what about safety? How do we know a drug is safe before, testing it on people?
That's where 80/80 prediction comes in. We can use computer models to assess how a drug will be absorbed, distributed, metabolized, and excreted, as well as potential toxicity, all before we even get to those costly and time-consuming lab tests. It's a huge advantage.
That's incredible. So we've been talking a lot about pharmaceuticals, but you mentioned that chemoinformatics has applications beyond just medicine.
Oh, absolutely. It goes way beyond pharma. Think material science. Chemoinformatics helps us design brand new materials with specific properties, like better conductivity for electronics or stronger, lighter polymers for construction.
Wait, so these computational tools can design something as tangible as a building material?
Exactly. By predicting how different molecular arrangements will behave, we can essentially design materials from the ground up. And it doesn't stop there.
Oh, there's more. Lay it on me.
Chemoinformatics is also making waves in environmental science. It's used for toxicity prediction, assessing how dangerous certain chemicals are, and for environmental fate modeling, predicting how pollutants will spread in the environment.
So understanding how molecules interact not just in a controlled lab setting, but out in the real world. Fascinating. What about agriculture? Any applications there?
Oh yeah. Chemoinformatics is helping us design new pesticides and herbicides, aiming for greater effectiveness and, crucially, less environmental impact.
So we're talking about tools that can impact pretty much every aspect of our lives. What's the tech behind all of this? What kind of tools are we talking about?
We're using specialized software like RDKit, programming languages like Python and R for analysis, and of course, machine learning algorithms are key for those powerful predictions.
And I'm guessing this field is, pretty dynamic, always evolving. What does the future hold for chemoinformatics?
Oh, it's definitely a fast-moving field. We're seeing huge advancements in AI and deep learning, allowing us to handle even larger or more complex data sets. Plus, cloud computing is making these powerful tools accessible to more researchers. And there's a big push for open source tools and making chemical data more findable and usable.
So it's all about breaking down those barriers and democratizing access to this powerful technology.
Exactly. It's really exciting to see where the field is headed.
So to recap, chemoinformatics is this incredibly powerful fusion of computing and chemistry, giving us these incredible insights into the molecular world, from the medicines we take to the materials that shape our lives.
And it's only going to become more important as we continue to unlock the potential of chemical information across these diverse fields.
It's mind-blowing to consider how this connection between computer science and traditional sciences will keep transforming industries and what kind of unexpected breakthroughs we might see in the years to come. Thanks for joining us on this deep dive. It's given us a lot to think about.